And notice that was the whole problem, having this plugged into the wall, okay? We can extend vectors in 3 dimensions, so many of those same concepts from 2 dimensions just apply directly to 3. You just have to add on a 3rd coordinate. So it's going to be very handy. Because some of our other options don't work so well. How do you set up a 3D system from a 2D system? Here's our 2D system that you've been used to, an x and y axis. It's a plane map. Now we're talking about what happens in 3 space, and that's where the Oompa Loompas come, okay? So I want to explain to you because a lot of people wonder why it's set up the way it is, and why the x comes down this way, right? Why is the x in this direction and the y in this direction?
We are recording.
Okay, here's how it works. Here's your x-y coordinate system. If you put your right hand in the x direction and your left hand up in the y, right? Woo! That's a plane, right? You only have 2 dimensions.
This is a plane.
Now,
Awesome.
how do you do it with the Oompa Loompas? You ready, John?
Yeah. Oh wait, I gotta record him.
Catch that, okay? So we're flat against the wall.
Loompa.
Now you see where the axes are. This is the x-axis then. Awesome. This is the y-axis. Where's the z?
Foot.
No, my head is the z.
Oh, it's...
That's how you do it. Cut. Now, let's practice blind to point 2, 3, 4. Because it can be very tricky. Blind to point 2, 3, 4. Well, remember how you used to do 2, 3? You go over 2 and up 3. Focus. So now to do 2, 3, 4, we want to go 2 in the x direction. So that's 1, 2 in the x direction. Now what point are we at so far?
2, 0,
2, 0,
0.
0. 2, 0, 0. Because you haven't done any motion along the other axes. And then we're going to go 3 in the y. That's in this direction. So 1, 2, 3 in the y. Now you're at the point 2, 3, 0. And then finally, let's go 4 up. 1, 2, 3, 4. And now we're finally to the point 2, 3, 4. This is sort of the trick using lines to connect them like this. So there's our vector. Now, looking at that vector, how can you tell that it's not just right in the YZ plane? Well, it comes out a little bit. These little angles are supposed to help you see that we're into the first octet.
Can you like make the grid part darker?
The grid part darker, I can try.
Oh, what did Andrew do last time? You made the grid darker in class last time, remember?
You guys said fill.
Right. Oh, well, no, because I pasted this as a whole thing here. Sorry.
But I lost it
Yeah, how did you go up? Because I got the grid.
Shh, quiet, please.
Do you follow the same line, or do you just go up?
You start from the origin out to the point where we stopped.
No,
We will follow the same line.
from going to 2, 3, 0
To 2,
to 2, 3, 4.
3, 4, I went straight up in the z direction, 4 units. So I took this length of 4 units and went that
You
much.
don't follow the line and then go up?
Follow what line?
Like it makes sense in like wait.
Which one?
Okay, so
it's supposed to go.
it's like you don't. Is that the tell? Just go up.
No, because with that line, you're going to follow along the axis.
Yeah.
You're going to go parallel, you're not going to actually see it right exactly on one line. So you're going to take a vertical line like that.
Remember the 4 goes?
Yes. I mean, you can measure with your hands 4 along the z-axis and then translate that going up 4 from here.
Wait, so you're really only going up? But I mean, like, it's. Yes, so it's like 1.
No, that's because you're looking at the YZ plane. This point on the YZ plane, if I didn't come on the x at all, that'd be only 0 over on the y, 1.5, and up on the z, 3. So you have to realize that's the problem with 3D graphing, is that it's still on a plane surface.
Yeah.
So there's going to be an infinite number of points that can basically represent that same dot on our 2D plane and project it onto it. That's why I prefer actually the box technique, which I'm going to show you next. We're going to do this again, but this time actually have a 3-dimensional box so you can see it. So a lot of people mistakenly think that this is, 2 on the x, 3 on the y, 4 on the z. 1, 2, 3, 4 on the z. And then they actually kind of connect the dots. Now we're going to see that that would be the plane that goes through 2, 0, 0, 0, 3, 0, 0, 0, 4. So don't just connect the dots here. You're not creating the point. You're creating a plane that goes to the point 2, 0, 0, and so forth. So instead what we do is we create a box. And it's a series of rectangles and parallelograms. For instance, if you just looked at this YZ plane here and put this point in right here, what is that point right here? 0 in the X, 3 in the Y, and 4 in the Z. There you go. Now we can do the same thing here with the parallelograms down here and stay in the XY plane. So what's this point right here? Recall that this point was 0, 3, 0, right? And this point was 2, 0, 0. And this point was 0, 0, 4. 0, 0, 4. So what we've got in this corner here? 2, 3, 0. And we can do the same thing over here too. In the XZ plane to come up with this point. 2, 0, 4. So we basically have almost all the corners of the box, and of course the origin 0, 0, 0. What we want is the point in the box opposite from the origin. And this is where your skill comes in, okay? Right about there, correct?
Yeah.
And that's the problem we had before, because it doesn't go along any of the grid lines. Because we're going to have to go over from this, up from 2, 3, 0, back from 0, 3, 4, and see how they all come together in that point right there. No, the third dimension. Thank you. And that's the point we're looking for, 2, 3, 4. 2, 3, 4 is the point that's sort of the opposite corner of the box from 0, 0, 0. Not right now. And again, so now when I draw the same vector that we had before, it has a little more visual reference to it. Okay? Okay? You're going from the origin out to 2, 3, 4. Now, I wanted you to do this so you have a sense of the three-dimensional space. And also a sense for the type of equations for planes we're going to end up in the next section. I am not going to test on this skill. I will look at your homework on this skill, but it gets a little frustrating for students sometimes. They have things to do whatever, but still, you should try doing this out so you understand the concepts of what these coordinates mean in free space. For instance, what is the equation of this side of the box over here? There's something in common to all 4 of these points on this right side of the box.
X and Z.
No. They all have a coordinate in common. What is it?
A 0.
No. 0, 3, 4. Look at all this. 0, 3, 4, 0, 3, 0, 2, 3, 4, 2, 3, 0. They all have what? Where?
The Y.
The y. I.e., y equals 3 is a plane.
Whoa.
Y equals 3 isn't the equation of a horizontal line anymore. In free space, y equals 3 is the plane, like this. Parallel to the XZ plane, which is y equals 0. Right, if you just set one variable equal to a constant, you're going to get a whole plane, not just a Yeah, so it's kind of backing up one from the side of the space. So if we're in 4 dimensions, then something like x equals 3 would be the space.
And then once become wireless.
Assuming
you're only on one of
Well, no, if you give the coordinates, all 4 coordinates of a point, it is equal.
Okay, so like everything kind of like upgrades one.
But not everything, as you just said.
Yeah.
But a lot of times with the equations, though, yeah, they end up upgrading to one with the 4. Okay, so let's give equations for the XZ plane. This y equals 3 is actually parallel to the XZ plane. How do I get the XZ plane by itself now? What's common to all these points? 0, 0, 4, 2, 0, 4, 2, 0, 0. The y equals 0. For the XY plane, z equals 0. For the YZ plane,
X equals 0.
the YZ plane is x equals 0. Okay? So, just set a variable equal to a constant. It doesn't give you a line anymore, it gives you a whole plane. That makes the axes hard. Remember, the x-axis is just y equals 0. That's how you found the x-intercept. You set y equal to 0. Now the x-axis, though, it's an equational line. If I just say y equals 0, that's going to give me the whole xz plane. I have to say y equals 0 and z equals 0. You actually have to give an equational line as the intersection between two planes. Okay? Now, we're also going to have equations for lines that involve a direction vector, too. We'll get that in a second. But in terms of what we're looking at now, we take the xz plane and the xy plane. The xz plane and the xy plane intersect to create the x-axis. And so that's why it's an intersection of these two. So how about the y-axis? X equals 0 and z equals 0. You got to make sure both those coordinates are 0. Now you know you're on the y-axis. And then the z-axis and y. Okay? Now, this is a good idea too, because sometimes you want what we call the trace in an axis, or if you want to find the z-intercepts, you set the other two coordinates equal to 0. Okay? If I want to find the trace of a plane inside a coordinate plane like the xz plane, I set y equal to 0. 3D in GeoGebra. No, I haven't been able to find that quite yet. Okay?
Try to get on it.
Yes, that'd be great. Okay, now I have to, oh yes, now we're going to do some equations of some of these other things. Distance and midpoint formulas, they're pretty straightforward. What's the distance between 2 points? Oh, I think I was going to try and draw the box here. See, you don't know where this point is. If I just put a point on my 3D diagram, that could be in the xy plane. It could be up and then over and then down and so forth. So just because I put it here, it could actually be, it could have a negative z, right? And come over in the x, come down z, and then back up y. So there's a lot of routes to that. But what I'm going to do is just make my standard old box like this. Box. Box. I'm sure you've done this in art class, right? You make two congruent rectangles, offset them, and then connect the corresponding corners. And now, depending on how you twist your eyes, that might be coming out at your India, but it's one way to clarify is to make the, get your micro eraser out, and go like this. Oh, dash these back lines. See that? I dashed the back lines. So that these are the lines you actually see. And those dashed lines are in the back and you can't actually see them. Except that this is an invisible rectangular parallel pipette. So if we go from point A, which is x1, y1, z1, out to point B in the opposite corner of the box at x2, y2, z2, you actually get there in 2 steps of the Pythagorean theorem. You can get to this intervening step right here, and then you find the whole distance by actually looking at the rectangle in here like this. Do you see how this one would be easy enough with the Pythagorean theorem in this right triangle? But now you actually form another right triangle inside here that has this. So it's tricky, but the upshot of the whole derivation is that it just adds another element onto your distance formula. To get between 2 points, what did it used to be? x1 minus x2 squared plus y1 minus y2 squared. And now, just don't forget the z's. z1 minus z2 squared. Okay? And that's your distance formula between 2 points. All right? Now, how about the midpoint then? Remember what was before? It used to be
1 plus x2.
right, the average of the x's. Notice we're adding now, because you're finding the average, and halfway between these 2 x's, this midpoint will have an x coordinate that's the average of these 2. And I have a y coordinate, which is the average of the 2 y coordinates.
And you need the z
And
coordinate.
don't forget the z coordinate, z1 plus z2.
Never forget to know the
Okay?
So, but you'd have to give us the
extent of the drawing. When we start doing spheres and that type of thing, free space, it's tricky. Okay. That starts getting very complicated. And so let's do this one. The sphere has points 8, -2, 3, and 4, 0, 7 as endpoints of a diameter. Find the center and radius r of the sphere. So what are you going to do for the center?
Midpoint.
It equals the midpoint of what?
Those AB.
Of AB, the diameter. What's true for circles now also true for spheres. Any diameter of the sphere has to go through the center of the sphere. So we take 8 plus 4 over 2, -2 plus 0 over 2, 7 plus 3 over 2. And that should give you 6, -1, 5. 6, -1, 5 is our center. And find the radius r. That's the center. What are we going to do for a radius? Can't divide what by 2, though? We've already started taking the average of the two endpoints, A and B. And so we've already done this. Now I know this is not a sphere. This is a cross-section of the sphere, the two-dimensional plane I'm dealing with. Okay? And so you've already found the center, C. What's the radius then?
What's the distance between C and A or C and B?
You can do the distance divided by 2, you go from C to B, either way. You can go from A to C. Let's see, B doesn't have any of those nasty, well.
Is AB a diameter?
Yeah, AB is the diameter, so if you divide the diameter in half. But let's actually go with that. The radius equals half the diameter. The diameter equals the distance for AB. So it's AB times the square root of 8 minus 4 squared plus -2 minus 0 squared plus 3 minus 7 squared. That way, if we made a mistake in finding our midpoint, it won't show up here, right? So if you can use original information, sometimes you can avoid some of those arithmetic mistakes. 4 squared plus -2 squared plus -4 squared. 1/2 of 16 and 4 and 16. Half of the square root of 36 is half of 6, which is 3. So we have a radius of 3. The diameter was 6, the radius was equal to 3. Now, can you come up with an equation then? For the sphere?
Yes, we
Based on what, right?
You can just take the center and the radius, so it would be x minus 6 squared, y plus 1 squared, and then cancel it.
Okay, let me write down that center again. It was, the center was 6, -1, 5.
6, wait, hold on. 6. There is 6. Oh, yeah, 6. Never mind.
So it would be
Well, it's a constant.
squared
X minus 6 squared.
plus, and then plus y plus 1 squared,
Yeah.
plus c minus 5 squared equals 9.
Right. Well, the square of that equals 3. And normally, this is using our distance formula, right? The distance between x, y, z in the center has to always be 3. Now you square both sides and you get a nicer looking equation for the sphere. What did this used to be? An equation? What was this like before? In 2D? When you square both variables. Circle. Now you're into 3 dimensions, so it's like that. Okay? Okay. Now, parametric equations really help in this. Find the equation of the sphere. We did that. So, here's their general formula for the equation of the sphere. Anybody generalize this one yet? General equation. Britt? Okay, let me help you. Z subscript 0 is called Z naught. Z naught. Easier said than Z sub 0. And then Y naught. Yeah, Y naught. Alright, now, let's just keep extending everything in the 3 dimensions. Our line equations, we had an equation for one line, that was the x-axis. But that was just based on a trick of intersecting 2 planes. You can do a vector equation line in any dimension, starting with the general point on the line. In this case, what's a general point on the line?
Y.
No. Let me start. X.
X naught.
No, not X naught. This is a general point on the line. X, Y, Z. The order triple. This represents a point on the line. Okay? Equals, now contains this point, so that becomes your starting point. X naught, Y naught, Z naught. Put commas in between there. Plus a parametric variable times the direction vector ABC. Okay? So it's just like the vector equation line we had in 2-space, except we've added a third dimension. Okay? Some of you look puzzled.
Puzzled with what?
Are you okay with this?
Puzzled with
That's our general equation we're doing a lot. We're going to have a specific example in a second here. In fact, there it is. Find a vector and parametric equation of a line containing 2, 3, 1 and 5, 4, 6. So we need a couple of things. You can use either point as your x naught, y naught, z naught, but the key thing is you need the direction vector. Which one of these should we use for the direction vector? No. 2, 3, 1 is not the direction vector.
You don't have to. You don't have
It
to.
goes, Emma, please tell me that.
Wouldn't it go through A?
Through A toward B. So you need both. You have to look at your direction vector is going to be AB. From A to B. Don't use either one. These two things are points. They're not direction vectors. To create the direction vector now you have to connect the dots, the vector between those 2 points. And then as you recall, to quickly calculate out the vector AB, it's B minus A. 5, 4, 6 minus 2, 3, 1. And so you get 3, 1, 5. That's your direction vector for the line. Yes.
Can you do negative?
You can have a negative in your direction vector.
Can you have like a negative starting one? Let's say A was like 2, negative 3.
Oh yeah. Yeah, you don't always have to be in the first option. A lot of times I do that so we can make a picture of it. I think we're going to try that in a second.
Okay, I'll wait.
So now for your equation, x, y, z equals, take either point, 2, 3, 1. We can use A or B here. Plus the parametric variable t times the direction vector 3, 1, 5. What does this mean in a picture? Well, this is where it's going to be a little tricky. Let's graph the 2 points in 2 different colors.
Yeah.
We got 2, 3, 1. 2, 3, 1 is going to be right in here, right? There's your point 2, 3, 1. I did it in red. See that one? That's just a quick sketch of where 2, 3, 1 is. You could have also gone over 2 and x, up 3, and then like that. Some people prefer that because it's faster, but sometimes it's hard to, as long as you know those little vectors are staying parallel to the axes, that's one way. Let's use some contrast here. In green, let's do 5, 4, 6. 5 in the x, 1, 2, 3, 4, 5 in the x. 6 in the y, 1, 2, 3, 4, 5, 6 in the y, so this is a bigger box, isn't it? And 4 in the z, 1, 2, 3, 4 in the z. So we end up with a much bigger box, and it looks something like this, right?
It's way too hard to draw.
Yeah. See, so there's 5, 4, 6. And so our direction vector went like this. That's your direction vector. And the line then continues off through those 2. Now you can see, you draw that line without any context, and you're not going to have any idea which way it's pitched. Now this gives you a little idea that it's the line connecting the opposite corners of these boxes here. Of course, not corners. Again, a little too much labor to put on a test, but I want you to understand the concept of what we're doing with all this manipulation of the points and so forth.
But if you gave us that question, we could just say x, y, z equals 2, 3, 1.
Yes, I would not expect a picture on something. Okay. So here's your basic vector properties then. Vector addition, u plus v. What do you do with the corresponding points?
X1 plus x2.
There you go. There you go. Scalar multiplication. Let's take k times u. K times x1, y1, z1. It just distributes k times x1, k times y1, k times z1. That's why sometimes I just use A, B, and C for some of these. The subscripts start getting confused with the commas. The magnitude of u, written like this, with the absolute value symbols. Or just leave the vector symbol off. That means the magnitude of the vector. Jack, what do you think? The magnitude of u.
What do I think it is?
Yes.
Oh.
I'm not doing the distance between 2 points.
X1 squared, square root of x1 squared plus y squared plus 2 squared.
Okay. So your twin responded. I'm not saying what Jack answered, okay? Why is this simpler than the other equation? Why is this simpler than the distance formula we looked at before? Because it had those squares of subtractions. Why is this different? It's the magnitude of a vector, which you're thinking of coming out of the origin, going out to that point, or you just look at the lengths of the side components of the vector. So that's why we can get by with this, and we don't have to do a subtraction. You're doing the magnitude of the vector. It's different than the distance between 2 points in 3 space. When you do 2 points in 3 space, what you're starting off with basically doing is figuring out the vector between them and finding the magnitude of that.
Because you're moving it, you're like kind of in a way to figure out the distance you're coming into the origin, so you don't
Right.
subtract it.
Okay, dot product. Jack, you want to take this one on? U dot V. Dot product.
Dot.
What would we do with the dot product before? We'll talk after class and see what your whole educational process is these days. Okay, anybody else? Ernest.
Would be x1, x2 plus y1, y2 plus z1.
Right. That's what it was before for 2-dimensional vectors, right? And now there it is tacked on the z1, z2. Finishes the dot product. Notice there are no parentheses around it. There's no commas. Because this is a scalar. You end up with a number when you take the dot product of 2 vectors in 3 space. And so the angle between 2 vectors in 3 space?
Cosine
Theta
equals x1 for the dot product.
Yeah, so you can just say the dot product.
Divided by
Sorry,
magnitude.
just UV divided by.
Magnitude of u. Magnitude of u.
Yeah, notice it didn't change. The formula didn't change. The dot product and magnitude formulas are a little bit more complicated, but still the same concepts applies even when we're in 3 space. So we can use that now to come up with the vector of equation of the line through 1, 5, -2, and parallel to the line this equation. Well, you saw how much work it was to try and graph one of these, to sketch these, so we're just going to get right into the problem. We want a vector of equation of the line. So what do you need for a vector equation? A direction vector and a point. So unlike before, way back in September, remember when we reviewed equations for lines, you needed a point and a slope, and there was our favorite point-slope form. This is like our new point-slope form.
Standard.
But instead of point-slope, it's point and direction vector. So we just need a direction vector. What are you going to use for your direction vector? Right, you borrow the one from here. If it's going to be parallel to that line, it must have the same direction. Now, if you want to, you can change it to -4, -3, -2, or 40, 30, 20.
Or 8, 6.
Or any scalar multiple of this would work. So xyz equals, now I need a point on the new line. Where's that hiding out? There you go, 1, 5, -2. Plus the scalar multiple, don't forget that part. This is what gives you more than 1 point. Okay. Times the direction vector 4, 3, 2. See, these lines are parallel because they got the same direction vector.
What if they were perpendicular? Can you even be?
Well, so for perpendicular, that's the trick. See, if I have a vector in 3 space,
Yeah.
this is perpendicular, so is this.
Oh.
So we're going to talk about a perpendicular plane to that vector. Or if I've got 2 vectors, we're going to create a vector perpendicular to both. Yeah.
How would you check, like, if it says, okay, is it, like, how would you check if a certain point
check if a point is on the line, you've got to look at the individual parametric equations and see if they're consistent. So you put 3, 1, 2 in for x, y, and z. And then you can create from that 3 equations in the one variable t. Now that's more than enough you need to find out t, right? But the trick there is don't just look at a pair of them, don't just look at one of them. Solve one of them, make sure it still is consistent with the other
All
two.
the T's have
Yeah.
to be.
All the t's have to agree.
Oh, wait.
So that's how you tell if a point is on a line or not. Put in the points for x, y, z. Like let's expand this. Let's expand the question here. Is 1, 5, negative 2 on the line x, y, z equals 8, 0, 1 plus t times 4, 3, 2? Well, we can answer the question easily if we started like doing addings odds to 8, 0, 1, but I don't think it's going to run into that exactly. Or we might be able to answer it exactly with him that does a decent picture, but you saw how much time that takes. So you say 1, 5, negative 2, set that equal to 8, 0, 1 plus t times 4, 3, 2. And then set up the different parametric equations. 1 equals 8 plus 4t. 5 equals 0 plus 3t. Negative 2 equals 1 plus 2t. That's an equals. So, negative 7 equals 4t. T equals negative 7/4. Don't just say, yes, oh, it happens that time equals negative 7/4. No, because now over here you get t equals 5/3. Inconsistent! That's like what you always were told you had to be in bed by 9 p.m. on a school night, and then your little brother now gets to stay up until 10. What? This is inconsistent, right? So, there you go. It's inconsistent, so therefore, 1, 5, negative 2 is not on the line. Okay? Good question, Rick. Glad you brought that up. That wasn't in the original video. But that does come up in the homework a lot. Making sure that you actually have a point that's on the line you're looking for. Okay, angle between two vectors. Ooh.
Oh, are you good?
Not a problem. We can just go cosine theta. Don't try and draw these, and then you got your two boxes, and then you're trying to look at the angle between the two boxes.
Oh, no.
You try to measure with a protractor. No, because the protractor's not in the plane of those angles. It's in the plane of your screen. So, yeah, that technique would not work too well.
No.
So we take the dot product, 7, 0, negative 1, all over the product of the magnitudes. So 4 squared plus negative 5 squared plus 3 squared, square root of 7 squared plus 0 squared plus negative 1 squared. So the dot product, help me out with the dot product here. Who's ready to help me out? Keep everyone the same 3 people. Same 3. Let's have the dot product here.
So you do 4 times 7.
28
Yeah, plus 0. Is that
plus 0, I guess that's 0.
or plus negative 3.
There you go. Okay, how about the magnitudes here? We got the square root of 16 and 25 and 9 times the square root of 49 and 1. So you're getting 25 over the square root of 50 times the square root of 50. Wasn't that handy? 25 50ths.
Oh, then it works.
1/2.
Don't say no.
So the cosine theta equals 1/2. Now, are some of you whipping out your calculators at this point? Seriously? It's
Oh my goodness.
Thank you. Thank you for remembering some of your tricks.
Yay!
Just give me
The light is
angle between 0
on.
and 180.
These will always be 0, 180.
Yes. Because yes, you could measure the angle by going around in 3 states this way, but we just want these small as possible between those 2 vectors. Okay. I think that's just about it. Oh yeah, look at all these people that have committed now. Emma, last year, Sean, 1720.
Yeah.
Put that up again. All right. Just gonna flange out here for a second here.
We submitted a lot of
Wedge out.
Wedge out.